Let's discuss rotational inertia. So we know from the past that F equals ma. That's how mass is important, because it determines how much acceleration is going to respond to the force applied. And we also have this torque tau equals I alpha. This is torque, and that is rotational inertia. So this is how important it is to the rotational dynamics that the response, the angular acceleration is determined by how much rotational inertia you have against how much torque is applied to you. Okay, so let's get started calculating what this value is. This depends on the system. So let's first start with a point mass. Okay, so how often do we see a point mass rotating around a point at the center of a circle? Well, not often, but we're actually on planet Earth, and to our star, the Sun, we're pretty much a point. We're so far from the Sun that our radius or diameter of the planet is very small. So we can consider ourselves as a point. So now we have here another point. This is the Sun. And here, this is us, Earth. So we're rotating around the Sun. So let's draw this kind of elliptical version of side view of rotation. So we know that this radius is much larger than our tiny teeny planetary radius r here, right? So we can pretty much consider the Earth as a point mass in the larger scheme of the planetary motion, right? So now we have a point mass. It's effectively a point mass if you're calculating such interactions. So what is the rotational inertia of a point mass? This is actually easy. The formula, let me write it below here, is rotational inertia equals mass, not the lower r, but the uppercase r squared. So the mass of the point mass, this is the distance to the axis rotation. So let's draw this axis tilted, well, to some observers, we might be doing that, right? So this perpendicular distance to the axis of rotation. All right, so we're rotating around this axis, and this perpendicular distance is r. So we need to remember that r is perpendicular distance. We can't just use any distance. The perpendicular distance, perpendicular to what? To axis of rotation. So you have a point here, excuse me, and you also have a line here. So the distance between a line and a point is just draw this perpendicular line, right? So let's have a practice on that, because sometimes it could be confusing. So let's just draw an axis of rotation here. And we have this point mass right here. So I want the r value. So is this the r value? And you may notice that this is not even perpendicular. If I extend this line, and that's not perpendicular, right? So this is not the perpendicular radius we're looking for. We're looking for this, right? So this is r. So that's not correct. This is correct. So we're always looking for a perpendicular distance. Assuming this point is going in and out of the plane, trying to rotate around this axis of rotation. Although I didn't draw the axis long enough, this could be a limit of, say, there's an actual axle, and this could be a string, and you're just spinning this this slingshot, and the physical shot here is not at the same level as this point, or it's kind of below that level. So you're spinning the thing. So it physically looks at this handle here and that shot. So they may exhibit this shape. And you don't want to just draw this line and say, oh, that's the string there, and that has to be the distance. No, it's not perpendicular. We're looking for this, right? So that's a perpendicular distance. And okay, now we have rotational inertia of 1 point mass. What about if we have a system of point masses, just as our 8 plus planets and the dwarf planets, right? So we have a multitude of objects orbiting the sun at different radii, different perpendicular distance. So if you have a system of point masses, and then each point mass will contribute to rotational inertia of our system. The sun does not contribute because, well, it's so small compared to its distance to all the other objects, the planets or whatever other objects orbiting the sun, say maybe a comet, right? So this m here, all the masses, right, I equals 1 through n, all the masses in the system, each mass and its own perpendicular distance to the axis of rotation. So we have a large sum here, and this sum is basically, each mass is independently contributing. So this could be m1 r1 squared plus m2 r2 squared plus the rest of the masses, right? So this could be, the last term is m, the last one n, rn squared. So depends, right? If you just want to calculate the rotational inertia of all the planets around their axis of rotation, you can calculate this way. They may not exactly rotate around the same exact axis, though. You may want to check your astronomy textbook to see how far the axes are from each other. But this is an idea. If you imagine all the planets are on the same plane, rotating on the same plane. All right. So this is relatively easy. Let's see if we have an example. So we have a mass 1, 2 kilograms, and some distance. Say x1 equals, this is an xy coordinate, 2, and y1 equals 5. And then we also have m2. 1 kilogram, make it easy. x1 equals minus 4. Sorry, x2. Then y2 is equal to 3. Okay, so we can imagine where they are, 2, 5, right, and minus 4, 3. So we have this tiny little diagram indicating where things are. So 2, 5, and minus 4, 3. Okay, and this is our x-axis, this is our y-axis. So the question is the rotational inertia of the system around the x-axis. So what is Ix? Alright, first of all, we need to find the perpendicular distance, the distance to the axis of rotation we just picked, the x-axis. So the x-axis is lying right here, and this mass's perpendicular distance is exactly its vertical coordinate, right? So that is 3. And that one over here, vertical coordinate, which is 5. So we're actually using the y-coordinate because it happens to be just the distance to the x-axis we're looking for the rotational inertia around, right? So this is I1 plus I2, 2 masses, so m1 y1 squared plus m2 y2 squared. So you may want to pause the video and use your calculator for the answer. Okay, we're back. So m1 is 2 times y1 is 5 squared, m2 is 1 times y2 is 3 squared. So we have 25 twice that 50, this is 959. And the unit worth mentioning is kilogram from the mass and meter weight squared, right, for the distance squared. So the unit, kilogram dot meter squared. Okay, so that is the rotational inertia around the x-axis. So let's ask a second question, rotational inertia around the y-axis. So now the distances will have to change. M1 is this far from the y-axis, exactly x1 away. M2 is exactly x2, well, minus x2 away. Since we're squaring the coordinates, it doesn't really matter. So now I1 plus I2 involves M1 x1 squared plus M2 x2 squared, because the x coordinates now serve as the exact distance to this new axis of rotation. And we'll do this again, 2 times 2 squared plus 1 times 4 squared. I never square negatives. It's easy to make a mistake if you do that. Okay, so that's a 4 and 8, and 4 squared is 16, so 16 is 24 kilogram dot meter squared. So let's see, we have two separate values. It looks like the rotational inertia really depends on which axis you're rotating around, isn't it? It could have many different values, and maybe in later parts of the video, videos, I can tell you there are several values along certain axes, and other values along arbitrary rotational axis can be calculated from these values. But you just imagine, if you draw an arbitrary axis, you'll have some arbitrary distance from that axis, from the points to the axis, and then the calculation will change due to the distance is different. Okay, so now you might be wondering why I squeeze all that calculation on the bottom left while I have half the page still empty. That's because we want to discuss the 2. So 1 is point mass. What about 2? So 2 is not point mass anymore, it's a rigid body. Okay, a rigid body is actually made up of point masses, and they have to translate and rotate together. So we're only discussing regular shapes, very regular shapes. If you want something slightly off regular shapes, you will need further calculations based on rigid bodies and also point masses. So let's discuss something regular, just regular shape. Say the pen that I'm holding in my hand. So I'll draw an axis, and okay, when I was in high school, I love to spin my pencil. So right here, spinning a pencil. If you know how to spin a pencil, the pencil kind of spins around your hand. This is how it would go around your hand, and the pencil has length L, and it's relatively thin. So we're basically ignoring the dimension, the cross dimension here, and we'll give it a mass m. So if I'm spinning my pencil through its symmetrical axis like this, so what is the rotational inertia? Well, this value is related to the mass, related to the length. As we have already discovered, the unit depends on mass and the length squared, except that there is this factor here in front, and this factor is 1/12. So why exactly the 1/12? Well, I can't really tell you right now, but what I can tell you is, imagine this whole bar is a collection of point masses, very small sections that you cut out, right? Smaller sections. So each section is a point mass. It has its own distance to the axis rotation. Well, only these two sections on the far end, these end caps, have the farthest distance, half L, right? If you square that distance, you get a quarter of an L. So there's only two end caps that can get about quarter an L times their own mass. And the rest of them will have less of that distance. And if you square that shorter distance, say this piece right in the middle of the left section, so that will be a quarter of an L instead of half L. And if you square that quarter L, you get what? You get 1/16 of an L, right? So you can imagine the importance or the contribution of each of these pieces is getting dramatically reduced as you go to pieces that are closer to the axis of rotation, because the distance is squared, right? So over here, the half of that distance is a quarter L. You square that into 1/16, right? So if you can put all the contributions together and double it up, because there's the other half on the other side, then you actually get this 1/12. Right, it doesn't really make sense yet, but you'll have an idea that how you would be able to do it if you were to cut this shape into small pieces, and each one you keep an account of the distance. You add them together using this formula. All right, so let's move on to another example. So here we have again a rotational axis. Redraw this. Okay, so here is another rigid body. This is no longer a pencil. Just imagine you have a bat, a baseball bat. You're swinging the bat, so you're holding almost the end of the bat. And although the bat is not very uniform, this is a uniform rod. So if you're holding over here, then compared to that, even if they're exactly the same length and same mass, you can imagine this half of it is having the same contribution as this half. But this half, on the other hand, is further away compared to where this half is, closer by. So it must contribute to a larger amount of rotational inertia than what this can do, right? So as a result, we'll have a different fraction here. Still ml squared. This is kind of extent L, right? ml squared. Now you have 1/3. 1/3 is actually 4 times as big as 1/12 already. So the contribution of this thing moving away from an axis rotation is quite obvious. So this is rotating around a different axis, as you have already noticed in the previous example. Rotating around a different axis gives you a possibly different rotational inertia. Okay, so let's go on to the next. Okay, here we have a third object. This object, I promise you, is easier, although it may be difficult to actually see what I'm drawing. I'm trying to draw a ring here. Let me thicken my drawing a little bit. I know this might not be the best way to do it. I might be better off with a thicker stroke pen, but trying to make it look okay. So it's actually a ring. All right, so the ring is actually sitting flat in this kind of axis. I tilted up a little bit, just the view, so that the ring's still flat, just the perspective is tilted. So we're actually rotating the ring around itself. So just imagine this were say a bicycle tire. This is kind of a through the axis of the bicycle here. You're trying to rotate the tire. Okay, so go around this. Here you have a radius, and you have a mass, and the rotational inertia is actually this mr squared, actually just a 1. Okay, so why is that just a 1? Well, you can imagine cutting the ring into small slices, right? So how far is each slice to the axis of rotation? Exactly radius r. Exactly radius r. So all the slices you can make, they have the same distance to the axis of rotation, exactly r. So that makes the sum just basically summing all the masses together, the small slices you slice together, you slice into these little pieces, right? So they all have the same distance. Unlike these shapes, all the other pieces have different distances to the axis of rotation. So this should be easy. Everything is the same distance. Okay, we'll have that distance and total mass. So mr squared. So that is that. It's just like you have a point mass held at r radius or distance away from the axis of rotation with the total mass of the ring. All right. So now we have a ring, and we'll have a second object. Okay, so here is a disc. Okay, so now the ring has turned into a penny. So we're not really spinning the penny the way you think. We're just basically putting the penny on tabletop and try to actually kind of rotate it while it's on the tabletop, not spinning a coin like you usually do. All right, so we're rotating it. Just like we can actually imagine this were actually a large portion of a top. So we're kind of spinning the top on tabletop. So that's what it's doing. Okay, right. So let's get rid of whoa, too much. It's dangerous. Too close. Okay. I guess that's the issue with strokes being strokes instead of just lines that I erase. Okay, so we have a disk. So what about the disk? The disk also has a radius r and a mass m. So the rotational inertia, as you may imagine, mr squared, but here is a 1/2. Okay, so why is a 1/2? Well, you can imagine the disk is actually a collection of concentric rings, right? So you can have a ring here. This is an arbitrary ring. There's another ring here, right? There's also the outer ring, and only the outer ring has its mass at radius r away. All these inner rings have less and less radius, so they count or they contribute less and less. Although they all have masses, their distances are getting shorter and shorter and shorter, closer to the axis of rotation, and somehow they just add up to less than a 1, right? They have to add less to a 1. So it ends up being a 1/2. All right, I promise this will end pretty soon because I'll run out of space, right? So what if we have a sphere? Okay, so let's call it solid sphere. We have radius r, we have mass m, and this is a solid disk. This is a ring. Okay, so we have this. We'll also have I equals mr squared. And before I write the answer out, I'll add another shape here. This is no longer a solid sphere, but it's just a shell. So all the mass is located or concentrated at the shell, and the inside is empty. All right, so we have a shell. The shell also has a radius r and mass m. And the rotational inertia is mr squared. And as a student, I found myself making this comparison between these two, and I always remember this 2 on the top, and I can't really remember what was on the bottom. And I know that there was a number 3. There's also a number 5. They go into the denominators. So which one goes where? All right, so I know that 2/3, 2/5, right? So 2/3 is greater than 2/5. That means somehow this, well, it's bigger, so it should be associated with one object, the object that has a larger rotational inertia. So let's think about this. Let's think about the solid sphere. So we can say that the solid sphere is a collection of concentric shells, right? So if we have a value for the shell, then the next shell, the smaller and smaller. So let's draw a smaller shell here. Okay, here's a smaller shell. So the smaller shell will have a smaller radius and much smaller rotational inertia. Besides, the mass may be smaller, then the radius gets squared, right? So smaller and smaller and smaller. That means not all mass is pushed to the far large sphere, large shell as possible. So then the smaller shells embedded inside the biggest shell will contribute less than if they were pushed all the way to the biggest shell. So this is a less effective way to get a large rotational inertia. And so this must be a smaller value. So now my reasoning is working. And now we can remember this as, well, that is a less effective way to distribute mass as far as possible compared to this, which pushes all the mass as far as possible to this largest shell, right? So this is more effective, a larger value. This is less effective, a smaller value. We can also have the same conclusion between these two. More effective way to have a larger rotational inertia is to push all the mass to the rim, and less effective is to have this disk. So this is a very short introduction to rotational inertia, the point mass on the left side and the rigid body on the other side, with the help of the point mass formula here. And we can imagine, for example, if you want a large rotational inertia in your system, say you're a designer, you're trying to design something, say a flywheel, and you would probably pick the ring, right? You will pick the ring, you put all the mass that you are able to accumulate on the ring. Maybe you have some spokes, right? Have the spokes here. Instead of putting all that mass into a disc shape, because that has a less rotational inertia, and the flywheel is actually a device to stabilize rotations. So to stabilize rotation means you need larger rotational inertia to resist the sudden change of angular velocity. So you want larger rotational inertia, which means given the same amount of material you're willing to factor in the cost, you want to push that material to the ring to make the best out of it. And if you want to design something that can spin fast, on the other hand, you may want to reconsider, you may want to do something that is a solid disk, or even having more mass in the middle. Thanks.